As we move into looking at HLM, Hierarchical Linear Modeling, we're first going to review one of the first statistical models you learned about, the one-way ANOVA model. This is because the first HLM we will look at is very closely related to that one-way ANOVA model. Here's an outline of what we'll be looking at in this video. We'll first review the statistical model for the one-way ANOVA. We'll then look at a convenient way of organizing the data that will facilitate calculating the summary statistics that are used in performing the analysis of variance. We'll then look at the particular calculations comprising the one-way ANOVA, and we'll see how to organize the results of the ANOVA calculations with the ANOVA Table. We'll then consider estimation in the context of the one-way ANOVA. First, we'll look how to construct point estimates of the treatment means. We'll then look at point estimation of the variance of the ANOVA model error terms. Once we have those components, we'll be in a position to construct confidence interval estimators of the treatment means. We'll then look at both point estimation and confidence interval estimation of a difference between treatment means. And finally, we'll look at how to construct confidence intervals of the ANOVA model error variance. So we've got a lot to do. Let's jump in. First, we'll review the statistical model for the one-way analysis of variance. The statistical model for an ANOVA with a one-way treatment structure in a completely randomized design structure can be written in the following way. Y sub ij equal to mu sub I plus epsilon sub ij, where the index I ranges from 1 up to t, where t is the number of treatments, and the index j ranges from 1 up to n sub I, where n sub I is the number of experimental units receiving the ith treatment. Now, y sub ij is the measured response on the jth experimental unit receiving treatment I. Mu sub I is the population mean response under treatment I. And epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. Now, because this representation is expressed in terms of the mu sub i's, this is called the means model of the one-way ANOVA. The statistical model for this one-way treatment structure in a completely randomized design structure can also be written in the following way. Y sub ij equal to mu plus alpha sub I plus epsilon sub ij, where again I ranges from 1 up to t and j ranges from 1 up to n sub I, for each I going from 1 to t. Again, y sub ij is the measured response on the jth experimental unit receiving treatment I. Mu is the arithmetic mean of the treatment means. So mu is equal to 1 over t times the sum I going from 1 to t of the mu sub i's. Alpha sub I is the fixed effect of treatment I, where alpha sub I is equal to the difference between mu sub I and mu, and where the sum of the alphas is equal to 0. And then again, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. The error terms, the epsilon sub ij's, are random variables with mean 0 and variance sigma squared for all I and j. These error terms are assumed to be stochastically independent. In addition, for purposes of inference, it is usually assumed that the epsilon sub ij's are normally distributed, so that the epsilon sub ij's are distributed IID normal with mean 0 and variance sigma squared. Now, note that these assumptions imply that the random variation associated with the experimental units is the same under all treatments. Next, let's look at convenient ways of organizing and summarizing the data for a one-way ANOVA. The data for a one-way ANOVA is conveniently organized in tabular format, one column for each sample, or in other words, for each treatment level. The required sample summary statistics are then computed as column summary statistics. The required overall summary statistics are computed as overall table summary statistics. This tabular format is shown on the next slide. So we can see here that the columns correspond to the treatments. We have T treatments, and so in the body of the table, we have T columns. The rows in the body of the table correspond to observations. And then at the bottom of the table, we have a number of rows of summary statistics calculated for each column. We have a row for the sum, a row for the number of reps or the sample sizes for each of the samples. We have a row for the sample means or treatment means. And finally, we have a row for the sums of squares. And then over on the far right, in those summary rows, we have corresponding summary statistics for the overall sample. Now here is another way of representing the bottom row, essentially, the sums of squares. We're going to be using this notation, USS, for uncorrected sum of squares in subsequent calculations. And so I wanted to show you in this table where those values go. Next, let's look at calculations for the ANOVA. Let's start off with an analogy with the sample variance. Recall that the sample variance, S squared, is given by S squared equal to, and then this quantity S sub xx divided by n minus 1. Now the numerator, S sub xx, is the corrected sum of squares. It's the sum of the squared deviations of each observation from the sample mean. Now, the corrected sum of squares can be decomposed into a shortcut formula, or what we might call a computational formula, that is typically easier to use. And that computational formula consists of the uncorrected sum of squares, so the sum of the squared x values, which we can also represent as USS, uncorrected sum of squares. And then from that, we subtract what's called a correction factor. And so we can see that in this formula, the correction factor is equal to 1 over n, the sample size, times the square of the sum of the observations. We can also denote that for brevity by capital C. And this is going to be the way that we represent a corrected sum of squares in subsequent calculations. Note also that the denominator in the sample variance is n minus 1. Now, that n minus 1 corresponds to or represents the number of linearly independent components comprising that corrected sum of squares. Even though there are n terms in that sum of squared deviations, because of the linear relationship between the actual observations, the x sub i's, and the sample mean, there are actually only n minus 1 linearly independent components in that sum. And that number corresponds to the, or is called the degrees of freedom for the corrected sum of squares. And so when we calculate the sample variance, we divide the corrected sum of squares by the degrees of freedom associated with that corrected sum of squares. So now we can apply this to ANOVA. We're going to use the same type of terminology and computational or shortcut formulas in calculating the various quantities needed to perform the ANOVA. This consists of the uncorrected sums of squares and then correction factors. And we're going to be using these kinds of computational shortcuts to facilitate partitioning the total sums of squares of the response variable into the sources of variation associated with the treatment structure and the design structure in the statistical model. Now, in order to perform an analysis of variance, the following types of summary statistics will be needed. We'll need the individual sample summary statistics. We'll also need the overall summary statistics. And you'll recall that these are easily obtained when we organize our data in tabular format as we saw before. The notation and formulas for these summary statistics are given on the following slides. So let's take a look. We'll need the treatment sample sizes. And so the number of observations for each of the treatments, I going from 1 to t, will be denoted by n sub I. So n sub I is the number of observations receiving treatment I going from 1 to t. We'll also need the treatment totals. And so to get this, we add up the responses for each treatment. Now, the treatment total for the ith sample is denoted by y sub I dot, and that dot tells us that we're summing over that second index. And so y sub I dot is equal to the sum j going from 1 up to n sub I of y sub ij. And we calculate this for each I from 1 to t. We also need the treatment means. To get these treatment means, we divide the treatment total, which we just saw how to calculate, by the treatment sample size. And so the treatment mean for the ith treatment, the ith sample treatment mean, is y bar sub I, and that's equal to 1 over the ith sample size, so 1 over n sub I, times the sum j going from 1 to n sub I of y sub ij. And then using the notation for the treatment totals above, we see that y sub I bar, or y bar sub I, however you want to say it, is equal to y sub I dot divided by n sub I. Again, I ranging over the number of treatments, so 1, 2, and so forth up to t. So these are the sample summary statistics that we'll need to perform the ANOVA calculations. We also need some overall summary statistics. And so we'll need the overall response total. To get this, we add up the responses for all observations for all treatments. We will denote the overall response total by y dot dot, because to get this, we are summing over both indices, I and j. And so this is the sum of the y sub ij's, where we have a double summation, I going from 1 up to t, and then for each I, j ranges from 1 up to n sub I. We also need the total or overall sample size, and this is obviously just the sum of the individual sample sizes, and so we're going to denote this by n. And then finally, we need the overall mean. And so to get this, we divide the overall response total, the y dot dot, by the total sample size, n. And so we can see here that we're going to denote this overall mean by y with double bar on top. And then I've given 3 formulas here that we can use for calculating that overall mean. Next, we need uncorrected sums of squares. And so first we need the uncorrected sum of squares for each treatment. We'll denote this by USS sub I. This is the uncorrected sum of squares for the ith treatment. And this is the sum of the squared y sub I values, where we're summing over the index j going from 1 up to n sub I. And we do this for each of our samples, each of our treatments. So I going from 1 to t. Next, we need the total uncorrected sum of squares. We will denote this by USS sub tot. And we can calculate this in a couple ways. If we have calculated the uncorrected sum of squares, so the USS sub i's, then we can just add those up, and that will give us the total uncorrected sum of squares. Once we have the uncorrected sum of squares, we calculate the correction term, which we will denote by C, and this is equal to the square of the sum of all observations in the experiment. And then we divide that squared sum by the total sample size, n. Now, once we have this correction term, we subtract it from the total uncorrected sum of squares to get the total corrected sum of squares. And so you can see the calculation here. We also need what is called the treatment sum of squares, which we will denote by SST. To get this, we calculate the sum, I going from 1 to t, of this ratio of two values, the numerator, which is the square of the sum of the observations for each of the samples, and so y sub I dot squared, and then we divide that by the size of the ith sample, n sub I. Once we've calculated that sum, we subtract from it the correction factor c, and that will give us then the treatment sum of squares. Finally, we need the error sum of squares. The ANOVA calculations partition the total variability in the response, SS tot, into the variability due to treatments, SST, and the unexplained variability, which we denote by SSE. And so the ANOVA calculations partition SS tot into SST plus SSE. And because of this, once we have the total sum of squares, SS tot, and the treatment sum of squares, SST, we can calculate the error sum of squares by subtraction. So the sum of squares error is equal to the total sum of squares minus the treatment sum of squares. Now, it's typically easier to calculate the error sum of squares this way rather than trying to calculate it directly. By virtue of this partitioning of the total variability in the response, the ANOVA procedure also partitions the total degrees of freedom into the degrees of freedom associated with treatments, which we will denote by df sub treat, and the degrees of freedom associated with error, which we will denote by df error. And so, again, this partitioning partitions the total sum of, the total degrees of freedom, df tot, into the sum, df treat, plus df error. And because of this partitioning, the degrees of freedom for error can be obtained by subtracting the degrees of freedom for treatments from the total degrees of freedom. And as it was for calculating the error sum of squares, it's typically easier to calculate the error degrees of freedom using this approach rather than trying to calculate the error degrees of freedom directly. So as you can see, there are a number of calculations that we have to do in order to perform an analysis of variance. And in fact, we're not done yet. We still have several more that we have to calculate. But I wanted to stop here and look at a very convenient way of organizing the quantities that we calculate in performing an analysis of variance. And the thing we use to organize those calculations is the analysis of variance table. So here is the analysis of variance table for a one-way ANOVA. More specifically, an ANOVA with a one-way treatment structure in a completely randomized design. And so you can see here that we have 5 columns. The first column lists the sources of variation in the model. And so in our model, we have the total variability, and that's partitioned into 2 components. The variability due to the treatment structure, which we'll denote here by treatments, and that variability in the response that is not accounted for by the model, and that goes in the row denoted by error. The second column is the number of degrees of freedom associated with each of those sources of variation. And so you can see here that for the variation due to treatments, where we have T treatments, there are T minus 1 degrees of freedom associated with that source. We also know that there are N minus 1 total degrees of freedom, N being the total sample size. And then to get the number of degrees of freedom associated with error, all we have to do is subtract T minus 1 from N minus 1. And so you can see here that for this one-way ANOVA, we have N minus T error degrees of freedom. In the next column, we have sums of squares. And so we can put the quantities that we've calculated, the treatment sum of squares, the total sum of squares, and the error sum of squares in this column. And so we calculate the treatment sum of squares, and we can put it in this location. We put the total sum of squares in that last row, and then once we have those, we get the sum of squares for error by subtraction. So SS tot minus SST. Next, we have a column for the mean squares. Now, we haven't looked at those formulas yet, but we see here how to calculate those. The mean square for treatments is defined to be the sum of squares for treatments by its degrees of freedom, T minus 1. The mean squares error is defined to be the sum of squares for error divided by its degrees of freedom, or N minus T. And then finally, in the F column, for this particular model, we only have one F statistic. And you'll recall that in an analysis of variance like this, the F statistic is equal to the ratio of the mean square for treatments to the mean squared error. Now we consider estimation in the one-way ANOVA model. We'll first look at point estimation of the individual treatment means. Recall that the means model version of the statistical model for the one-way ANOVA is given by the following: y sub ij equal to mu sub I plus epsilon sub ij, where mu sub I is the population mean under the ith treatment, I is the index for the treatments, which varies from 1 up to t, and then j is for the observations within a sample, going from 1 up to n sub I. Now consider the mean response in the sample receiving treatment I. This is denoted by y bar sub I and is equal to y bar sub I equal to mu sub I plus epsilon bar sub I for I going from 1 up to t. The term epsilon bar sub I in this expression is the mean of the error terms for the observations in the sample receiving treatment I. That is, epsilon bar sub I is equal to 1 over the size of the ith sample, n sub I, times the sum, j going from 1 up to n sub I, of epsilon sub ij. The observed sample mean, y bar sub I, is therefore the sum of the unobserved and unknown mean response under treatment I, which is mu sub I, and the unobserved and unknown average of the error terms associated with the observations in that sample, which is epsilon bar sub I. The goal is to estimate mu sub I, the mean response under each treatment, where I goes from 1 to t. Now from the expression for y bar sub I, it can be shown that the expected value of y bar sub I is equal to mu sub I. That is, the expected value of y bar sub I, which is the mean of its sampling distribution, is equal to mu sub I, which is the true mean response under treatment I. Now this implies that the sample mean, y bar sub I, is an unbiased estimator of the mean of the ith treatment mu sub I. Because of this, we'll use the sample mean y bar sub I as an estimator of mu sub I, and we will denote this as an estimator using hat notation, so that mu hat sub I, which represents our estimator of mu sub I, is equal to y bar sub I. And this is for each I going from 1 up to the number of treatments, which is t. Next, let's look at point estimation of the variance of the ANOVA model error terms. Recall that an unbiased estimator of the variance of the model error terms, sigma squared, is provided by the mean squared error, the MSE, in the ANOVA table. We will denote this estimator of sigma squared using hat notation, so that sigma hat squared, which represents our estimator, in fact unbiased estimator of sigma squared, is equal to MSE, the mean squared error from the ANOVA table. The corresponding estimator of the standard deviation of the model error terms, which is sigma, which will be denoted by sigma hat, is therefore given by sigma hat equal to the square root of sigma hat squared, or the square root of MSE. Now these estimators are based on n minus t degrees of freedom, which is the number of degrees of freedom for error from the ANOVA table. Now that we have those components, we're in a position to look at confidence interval estimation of the treatment means. Now, it can be shown that the true variance of the sampling distribution of the estimator mu hat sub I is equal to sigma squared, the model error variance, divided by the size of the ith sample, n sub I. The true standard deviation of the sampling distribution of mu hat sub I will be denoted in a couple of ways. SD, or standard deviation, with mu hat sub I in parentheses, and also sigma, again for standard deviation, with mu hat sub I in the subscript. And so the true standard deviation of the sampling distribution of mu hat sub I is equal to sigma, which is the standard deviation of the model error terms, divided by the square root of the size of the ith sample. Now, these are unknown because they depend on the unknown variance of the error terms. If we plug the estimators sigma hat squared and sigma hat into these expressions for the variance and standard deviation of mu hat sub I, we get estimators of the variance and the standard deviation of mu hat sub I. So we will denote the estimated variance by var with a hat on top, and also sigma squared mu sub hat I with a hat on top of that. And so that is equal to sigma hat squared divided by the size of the ith sample, which is the MSE from the ANOVA table divided by n sub I, and the estimated standard deviation or standard error of mu hat sub I will be denoted in a couple of ways as shown here. So SD with a hat on top, and also sigma with a hat on top, and that piece of notation having mu hat sub I in the subscript. And so the estimated standard deviation or standard error of mu hat sub I is equal to the square root of the MSE divided by n sub I. So once we have these two pieces, the point estimator for the ith treatment mean, as well as the estimated standard error of that point estimator of the ith treatment mean, we can compute a 1 minus alpha times 100% confidence interval estimator for the ith treatment mean u sub I. That confidence interval is given by the point estimator minus plus, and then the estimated margin of error associated with that point estimator. Now the margin of error is equal to the product of an interval coefficient, which in this case comes from a t-distribution, and the estimated standard error of mu hat sub I. Now the interval coefficient, which is denoted here t with degrees of freedom and alpha over 2 in the subscript, this is the upper alpha over 2 percentage point of students' t-distribution with degrees of freedom equal to n minus t, which you'll recall is the number of error degrees of freedom from the ANOVA table. The estimated standard error of mu hat sub I, again, is the square root of the MSE from the ANOVA table divided by n sub I. Next, let's look at estimation of a difference between treatment means. An unbiased estimator of the difference between treatment mean I and treatment mean I prime, that is mu sub I minus mu sub I prime, will be denoted by putting a wide hat over that difference, and that unbiased estimator is equal to the difference between the corresponding point estimators of those treatment means. So mu hat sub I minus mu hat sub I prime. Now it can be shown that the variance of the sampling distribution of this estimator of the difference is equal to sigma squared times the quantity 1 over n sub I plus 1 over n sub I prime, and therefore the standard deviation of that estimator is equal to the square root of that quantity. So the square root of sigma squared times the quantity 1 over n sub I plus 1 over n sub I prime. Now, because these expressions depend on the unknown variance of the error terms, they are themselves unknown and must be estimated. Now note that if there is equal replication under treatment I and treatment I prime, that is, if n sub I equal to n sub I prime, then the formulas for the variance and the standard deviation of the sampling distribution of this point estimator of the difference between the treatment means simplifies to the following. So the variance of that estimator simplifies to 2 times sigma squared over n sub I, where n sub I is the common sample size, and therefore the standard deviation of that estimator would be the square root of 2 times sigma squared over n sub I. Now, estimators of the variance and standard deviation of the sampling distribution of this estimator of the difference are obtained by replacing the unknown error variance sigma squared in each of these formulas by its estimator, sigma hat squared, which again is the MSE from the analysis of variance table. And so the estimated variance of the point estimator of the difference between mu sub I and mu sub I prime turns out to be equal to the MSE times the quantity 1 over n sub I plus 1 over n sub I prime. The estimated standard deviation is therefore equal to the square root of that quantity. Again, if there is equal replication under treatment I and treatment I prime, then the estimators of the variance and standard deviation of the sampling distribution of that estimated difference of the treatment means simplifies, and so the variance, the estimated variance of that estimator of the difference is equal to 2 times the MSE over n sub I, and the estimated standard deviation of that estimator is equal to the square root of that quantity. Once we have the estimated variance and estimated standard deviation for that estimator, then we can use it along with the point estimator itself to come up with a 1 minus alpha times 100% confidence interval estimator of the difference between treatment mean I and treatment mean I prime. And this is given by the point estimator minus plus the margin of error associated with that point estimator, which again is the product of a interval coefficient from the t-distribution and the estimated standard error of the point estimator. The margin of error is equal to the product of this interval coefficient from the t-distribution and the estimated standard error of the point estimator. The interval coefficient is the upper alpha over 2 percentage point of the t-distribution with n minus t degrees of freedom. And again, this is the number of error degrees of freedom from the ANOVA table. The estimated standard error is the square root of the product of the MSE and the quantity 1 over n sub I plus 1 over n sub I prime. Now we're going to look at how to construct confidence intervals for the ANOVA model error variance sigma squared. Recall that the model error terms, the epsilon sub ij's, are random variables with mean 0 and common variance sigma squared for all I and j. The standard assumptions are that the error terms are stochastically independent with common variance. In addition, hypothesis testing about and confidence interval estimation of the parameters in the model are based on the additional assumption that the error terms, the epsilon sub ij's, are normally distributed. And so we'll use this in looking at how to construct confidence intervals based on the chi-square distribution. Now, one implication of this normality assumption is that the sampling distribution of the estimator of the error variance, sigma hat squared, or the MSE, when properly scaled, is a chi-square distribution. In particular, if we multiply the error degrees of freedom by the MSE and then divide by the true error variance, then that random variable has a chi-square distribution with degrees of freedom equal to the degrees of freedom for error from the ANOVA table. Now, this result can be used just as we used it in a first statistical methods class to derive one-sided confidence limits and a two-sided confidence interval estimator of the true error variance sigma squared. And so here are formulas that give us individual confidence limits for sigma squared, as well as a two-sided confidence interval for sigma squared. To obtain a 1 minus alpha times 100% lower confidence limit for sigma squared, we take the following ratio, the numerator being the number of error degrees of freedom associated with the ANOVA table, times the estimated value of sigma squared, which is the MSE, and we divide that by the upper alpha percentage point of the chi-square distribution with degrees of freedom equal to n minus t. To get an upper confidence limit for sigma squared, again at the 1 minus alpha times 100% confidence level, we take the same expression for the numerator, but we divide that by the upper 1 minus alpha percentage point of the chi-square distribution with degrees of freedom again equal to n minus t, the number of degrees of freedom for error from the ANOVA table. And then finally, to get a 1 minus alpha times 100% two-sided confidence interval for sigma squared, we construct a lower confidence limit and an upper confidence limit, each at a confidence level of 1 minus alpha over 2. So we've got to divide that alpha by 2 when we're going to put two of these limits together to get a 1 minus alpha times 100% two-sided confidence interval. These confidence limits are accurate and the confidence levels are exact as long as the assumptions about the model error terms are true. If the assumptions are not true, and in particular, if the error terms are not normally distributed, then the confidence limits and confidence levels will be approximate at best. The more closely the assumptions are to being met, the more accurate the confidence limits and confidence levels will be. An important thing to note is that the two-sided confidence intervals produced using this procedure are not symmetric about the point estimator sigma hat squared. That is, the lengths of the portions of the interval above the point estimator and below the point estimator are not equal as they are for intervals based on the normal distribution and student's t-distribution. In fact, the portions of the interval above the point estimator will be longer than the portions of the interval below the point estimator. Now, this is actually a desirable feature because it takes into account the right-skewed nature of the sampling distribution of the point estimator sigma hat squared. Because again, under this assumption of normality, the sampling distribution of sigma hat squared is a right-skewed distribution, in particular a chi-squared distribution. Now, this asymmetry of the confidence intervals will be more pronounced at smaller values of the error degrees of freedom. Again, this is desirable because the right skewness of the sampling distribution of sigma hat squared is more pronounced at smaller values of the error degrees of freedom. The confidence intervals will become less asymmetric, that is, be closer to being symmetric, although they won't be exactly symmetric. These confidence intervals will become less asymmetric as the degrees of freedom for error increases. Next, let's look at a method for constructing confidence intervals for sigma squared based on the normal distribution. Consider a parameter theta about which we would like to make inferences. Suppose an unbiased estimator of theta exists. Denote this unbiased estimator by theta hat. If the sampling distribution of theta hat can be approximated by a normal distribution, then the normal distribution can be used to develop approximate inference procedures for the parameter theta. This would include hypothesis testing procedures for theta as well as confidence interval estimation procedures for theta. The quality of the approximations provided by these inference procedures, for example, the true type 1 error rates of the hypothesis tests and true coverage probabilities of confidence intervals, will depend on how well the actual sampling distribution of theta hat can be approximated by members of the normal family of distributions. In the present context, our focus is on confidence interval estimation. If the sampling distribution of theta hat can be approximated by a normal distribution, then an approximate 1 minus alpha times 100% two-sided confidence interval estimator of the parameter theta will be of the following form. The point estimator, theta hat, and then minus plus the estimated margin of error, which is the product of an interval coefficient, in this case coming from the standard normal distribution, and the estimated standard error of theta hat, so sigma hat sub theta hat. And so the interval would be theta hat minus plus z sub alpha over 2 times sigma hat sub theta hat, where z sub alpha over 2, you'll recall, is the upper alpha over 2 percentage point of the standard normal distribution, and where the two pieces of notation sigma hat sub theta hat and then SD hat of theta hat represent the estimated standard error of the point estimator theta hat. That is, the estimated standard deviation of the sampling distribution of theta hat. Now we're going to be applying this general type of result to construct confidence interval estimators of sigma squared using the estimator sigma hat squared. The accuracy of the endpoints and the confidence level of this confidence interval estimation procedure will depend on how closely the true sampling distribution of theta hat can be approximated by a normal distribution. With this in mind, the next slide gives formulas for individual lower and upper confidence limits, as well as a two-sided confidence interval estimator for the variance of the model error term, sigma squared. Again, keep in mind that these are asymptotic confidence limits and confidence intervals, which implies the following. For any sample size, they are at best approximate. The quality of the approximation provided by these intervals is directly related to sample size, and as a result, their performance may be quite poor in small samples. And so here we have formulas for a 1 minus alpha times 100% lower confidence limit for sigma squared, an approximate 1 minus alpha times 100% upper confidence limit for sigma squared, and finally an approximate 1 minus alpha times 100% two-sided confidence interval for sigma squared. Now in two of these expressions you can see that we need to take the maximum of 0 and then some expression, and we need to do that because for small error degrees of freedom, that expression that we're multiplying against sigma hat squared can be negative. And so in that case, the lower endpoint, the lower confidence limit, would be a negative value. But because we know that sigma squared has to be positive, what we would do then is we would truncate it at 0. Now the confidence limits and the confidence levels for these intervals are asymptotic in nature, which means that they are based on derivations that allow the sample size to increase without bound. That is, by taking the limit as the sample size diverges to infinity. At any given sample size, they are only approximate, but the approximations provided by these intervals improve as the sample size gets larger and larger. The quality of the approximations provided by these intervals depends on both the sample size as well as the actual distribution of the error terms. For very large samples, the approximations provided by these intervals may be quite good. On the other hand, the quality may be quite poor in small samples. In addition, a sample size that may be large enough for these intervals to provide a good approximation in one situation or one application may not be large enough to provide the same quality of approximation in another situation or another application. This is because the quality of the approximation depends on the actual distribution of the error terms, and that can change from one situation or one application to another. Even if the error terms are normally distributed, even exactly normally distributed, the sample sizes needed for the approximations provided by these intervals to be accurate needs to be large. This is because the skewness in the sampling distribution of the estimator sigma hat squared needs to be attenuated in order for confidence intervals constructed using a symmetric distribution like the normal to perform well. With this in mind, note that the intervals provided by this procedure are symmetric. This is actually an undesirable feature when estimating sigma hat squared. For any sample size, the sampling distribution of sigma hat squared will have some degree of right skewness, but the method of constructing these intervals fails to take into account the right skewed nature of the sampling distribution of sigma hat squared. It is only as the sampling distribution of sigma hat squared becomes closer to being symmetric that the confidence intervals provided by this procedure become reasonably accurate, and that happens as the sample size gets larger and larger. The accuracy of these confidence intervals may be quite low in small samples. In such cases, their use is questionable. It would only be for larger samples that they will begin to be accurate, and therefore it is only for larger samples that they should be used and relied upon. So let's summarize what we've done. We reviewed the statistical model for the one-way ANOVA. We looked at a convenient way to organize the data, and we also reviewed the basic summary statistics that will be used in subsequent ANOVA calculations. We reviewed the calculations for the one-way ANOVA, and we saw how the ANOVA table helps organize the results of the ANOVA, but it also facilitates doing the calculations. And finally, we reviewed estimating the parameters and treatment effects in the one-way ANOVA model. We looked at point estimation of treatment means. We then looked at point estimation of the variance of the ANOVA model error terms. We then put these two results together to come up with confidence interval estimates for the treatment means. We also looked at point and confidence interval estimation of a difference between treatment means. And finally, we saw how to construct confidence interval estimates of the ANOVA model error variance. So we've done a lot, so I think we'll stop here. I'll see you in the next video.